In this video, we are going to introduce mesh analysis. This is a mathematical trick that makes it a little easier to analyze complex circuits consisting of a network of resistors, voltage sources, and even current sources, which we'll address in a future video. Now, this does require some basic knowledge of linear algebra and matrix multiplication, so if you are not comfortable with that, you can go back to the previous video and see how you can analyze this exact same circuit using the equivalent resistance method, which does not require any linear algebra, but does require slogging through a bunch of hand calculations and line-by-line algebra, which can get a little messy, so the matrix multiplication tends to make things a little simpler. So before we can do any mesh analysis, we probably need to define what is a mesh. So we are going to use the same example circuit that we had in the previous video with the equivalent resistance method. We're going to have a network with a single battery and a handful of resistors. So our battery is going to be Vs, then we're going to have R1, R2, R3, and R4. And a mesh is a loop within a circuit that does not contain any other loops. So a loop is a path you can trace where you start at one point and then wind up back at the same point. A mesh is a loop that doesn't contain other loops. So in this case, I can have a mesh 1 here that I'm going to label in green, and then mesh 2 that I'm going to label in red. But the outer loop, so around the outside of the circuit here, that is not a mesh because that contains 2 other loops. So meshes are just the inner loops here that do not contain other loops. I'm going to go ahead and erase that now so it's not in our way later. And for purposes of analyzing a circuit with mesh analysis, we are going to define what we call mesh currents. I'm going to use lowercase i's to represent those. So each mesh has its own current, I1 and I2. And these are mathematical constructions. They are not physical currents. This always confuses people when they see this and you go, okay, so you have mesh current I1 flowing in this loop and mesh current I2 flowing in this loop, but they're going the opposite direction through R2 here. So does that somehow mean you actually have electrons flowing in 2 different directions through R2, or 2 separate currents flowing opposite each other? No. R2 still just has a single current flowing through it that we will solve for later. I1 and I2 are just variables that we are making up that will make solving this circuit a little easier. Now, conceptually, that's very hard to understand at first. I think it makes a lot more sense once you see a worked example, which is what we're going to do in this video. So what we're going to do when I mention the linear algebra is we are going to find a system of equations AX equals B, where all of these are matrices and X is the matrix with our unknowns, so we can use linear algebra. We can multiply this entire equation by the inverse of A on both the left and the right, so that gets rid of the A over on the left side and gives us an equation X equals A inverse times B. And that is just a single matrix calculation that you can do with MATLAB or a graphing calculator or anything else that can multiply matrices. That gives you all of your unknowns at once, which again avoids that whole process of going through a bunch of calculations by hand and solving for them one at a time like we saw in the previous video. So what we're going to do here is have our same set of knowns from the previous video, which I'm going to copy over. We have Vs equals 6 volts, and then the 4 resistor values. R1 equals 1 ohm, R2 equals 8 ohms, R3 equals 7 ohms, and R4 equals 0.5 ohms. And we are being asked to solve for all of the parameters for R2. So we want V2, I2, and P2. And hopefully what we'll see is that you need to use the linear algebra, but that this trick makes it much easier than the process we saw in the previous video once you understand how to set up this system of equations. But once we do that, you should still get the exact same answer, so it kind of becomes a matter of personal preference as to which technique you like the best. Now, one more note before we continue. Depending on the website or the textbook where you look, you might see the mesh currents defined in opposite directions. So I drew them both clockwise here, but I have also seen textbooks that draw them alternating like this, with the idea that these currents kind of mesh like the teeth of gears, so they're both going down in the middle here, and supposedly that's where the name comes from. So it doesn't matter which way you do it, as long as you keep track of your signs, which we're going to talk about in a second. I learned it with all of them just going clockwise, so that's how I'm going to do it here. But if you want to draw them alternating or meshing, that is fine as well. So I mentioned signs, and that is where it's going to be very important to keep track of your passive sign convention, which we have an earlier video about. So you can kind of get away with ignoring that with simple circuits using the equivalent resistance method, which you saw in the previous video. But to do mesh analysis or node analysis, which we'll see in the next video, you need to go through and label the plus and minus signs on all of your resistors. And again, you can go back and watch the previous video about this. Physical resistors are not polar. This is just a mathematical definition defining which way positive current flows. So you can go through and pick these whichever way makes sense to you, and then as long as you keep track of the signs, you should still get these same answers. So I'm going to choose, kind of going from left to right here, plus and minus like this for all of my resistors, and we'll see where that comes in with our first step of this process, which is going to be applying Kirchhoff's voltage law to each one of these loops. So we are going to go through and apply Kirchhoff's voltage law, or KVL, to each one of these loops, and that is going to give us this system of equations where our unknowns are going to be I1 and I2, which then later we can use to solve for other things we were asked to find, like the voltage, current, or power of a resistor. So let's go through and do that for mesh 1 first. Now, again, I covered in a previous video, there are different ways you can apply Kirchhoff's voltage law, but as long as you are consistent with how you apply your signs, you should get the same answer or a mathematically equivalent equation at the end of the day. So the convention I'm going to follow here is I'm kind of going to start in the top left at the positive end of the battery, and I'm going to go clockwise around the loop. I'm going to add a voltage if I encounter a plus sign, and I'm going to subtract a voltage if I encounter a minus sign as I'm going around that loop. You might not want to do that. You might want to, for example, start here and say that batteries add voltage and resistors drop voltage, but at the end of the day, you'll mathematically get the same equation just with terms on opposite sides, but it'll mathematically be the same. So I'm going to start here. I'm going to say I have positive VR1. That's the voltage drop across R1. Again, remember, there's a difference between voltage drop across a resistor. In this case, that is measured between these 2 points. That is not the same as the voltage at a point referenced to ground. So when I use this notation, I am referring to the voltage drop across a resistor. I'm going to keep going around this loop. I am going to encounter this plus, so I'm going to add my voltage drop across R2. I'm going to keep going around the loop. I'm going to hit this plus. I'm going to add my voltage drop across R4. And then I'm going to continue going around the loop. I'm going to hit a minus sign now, and I'm going to subtract Vs, and I'm going to set all of that equal to 0 because, again, Kirchhoff's voltage law states that voltages around a loop must sum to 0. Now, again, I could have done that the opposite. I could have said I start here, go plus Vs, minus VR1, minus VR2, minus VR4, and hopefully you can see all that is doing is just flipping the signs on all of these, but if you move them to the other side of the equation, mathematically it's the same thing. So I've done that for mesh 1, and the next thing I'm going to do is I actually want to get this in terms of my unknowns I1 and I2, and I can do that using Ohm's law for each one of these. I know V equals IR, so I can use that to substitute in for each resistor to get this in terms of the mesh currents instead. And this is where you really have to start being careful keeping track of those signs. So we're going to do a quick recap of the passive sign convention here. If I have a resistor like this, where I have defined plus and minus like that, and that means I'm assuming positive current is flowing in that direction, and for Ohm's law, I have V equals IR, where if I define the voltages on opposite sides of this, VA and VB, that means I am assuming that V equals VA minus VB is greater than 0. So I'm assuming the voltage drops in the same direction that positive or conventional current is flowing. if I do this and I wind up getting a negative number for current, or I wind up getting that VB is greater than VA, that simply means that my assumption was wrong and current is actually flowing in the other direction. But that's okay. You don't have to know these beforehand. You just pick these and then be careful and consistent with your signs when you follow through with the math. And if you get a negative number, that's okay. So we need to remember, this is a little aside about the sign convention, need to remember that when we are going through for each mesh. So let's apply that to each resistor one at a time. VR1, we want to rewrite this in terms of a mesh current using Ohm's law. So for VR1, we are going to have, let's look at our mesh current and see which ones are flowing through R1. For R1, we only have I1 flowing through R1. So R1 is only a part of our first mesh here. And we see that the direction I've picked for I1 is already consistent with the direction for positive current for R1. So we have I1 is flowing into the positive and out of the negative terminal. So that is kind of just a long-winded way of saying for VR1, we just have that equal to I1 times R1. There's no extra minus sign in there. VR2 is going to be tricky. This one always tricks people up. So I'm going to draw R2 separately over here. So I've defined the signs for R2 like this. And over here on the left, I have I1 flowing down. But I2 was on the border between two meshes. And over here on the right, I have I2 flowing up. And remember, this does not physically mean that there are two different currents flowing opposite directions in this circuit, but that it means that according to my sign convention here, the net current flow through this resistor is I1 minus I2. So I1 is flowing in the positive direction, I2 is coming in the negative terminal. So again, remember my sign convention over here, current flowing the other direction is negative. So my net current flow here, which again, there is only a single current flowing through this resistor, is I1 minus I2. Okay, so for VR2, when I apply Ohm's law there, my current that I substitute in is going to be I1 minus I2 times R2. And then for R4, we have pretty much the same thing as R1. R4 is only a part of mesh 1, so VR4 is just going to be I1 times R4. Oops, I forgot my 1 subscript there. Okay, so there I have solved for all three of my voltages using Ohm's law in terms of the currents. I'm going to go ahead and plug those into this equation to get a single equation just in terms of my currents, where my currents are my only unknowns because I know all of the resistance values and I know my voltage source values. So that's going to give me I1 R1 plus VR2, which is I1 minus I2 R2 plus VR4, which is I1 R4 minus Vs equals 0. Now, keep in mind that our goal here is that we want to get towards a system of linear equations like this in matrix form. So we want a matrix that is only coefficients times a matrix of our unknowns equals some matrix of constants. So we want to do a little rearranging here, and I'm bad at doing math in my head, so I'm going to write it out line by line. We're going to write out I1 plus R1. We're going to expand this next term in parentheses here. That's going to be I1 R2 minus I2 R2 plus I1 R4 minus Vs equals 0. So we want to move things around here again to get it in this form. So we want some coefficients times I1 plus some coefficients times I2 equals other constants over here on the right. So we're going to consolidate all of our I1 coefficients into one term in parentheses here. That's going to be R1 plus R2 plus R4. Then coefficients times I2. We only have one I2 term, so that's going to be R2 minus, again, don't lose track of that minus sign, times R2 equals, now we're going to move this Vs to the other side. That is not a coefficient of an I term, that's just a constant standing on its own, equals Vs. So if you look at, oh, whoops, and I forgot to write my I1 there. That's important. Again, don't lose track of your variables. So once we get our second equation, that will allow us to put this in matrix form. So there is our equation for mesh 1. Now we are going to go and try and cram mesh 2 in on the same slide here. Let's see if we can fit that over here in this corner. Mesh 2, we are going to do the same thing. We are going to apply KVL around mesh 2. And mesh 2 is a little simpler. It doesn't have as much stuff in it. Again, I am going to start here and go in that direction. So I'm going to start here. That's going to give me plus VR3, so positive VR3. I'm going to keep going around that loop, and then I'm going to get minus VR2, and then I'm back to the beginning of my loop. I only had two things, equals 0. I'm going to write out Ohm's law for each one of my resistors. I'm just going through the exact same process here that I did for mesh 1. For R3, see R3 is only a part of mesh 2, so that is, and I2 is defined in the positive direction for R3, so that is going to be I2 R3, and VR2 is the same thing I had before. Again, don't get confused that I have this minus sign here. You don't want to double negative and add too many minus signs. VR2, based on the sign convention I have picked for R2, is the same as it was before. That is going to be I1 minus I2 times R2. So I'm going to plug both of these in here. VR3 is I2 R3 minus VR2, which is I1 minus I2 times R2 equals 0. I now want to do the same thing. Carefully expand these out because I am multiplying two negative ones there, so that is going to become a positive. So again, be careful with your minus signs. Just don't add an extra one at some point and then wind up flipping all the signs accidentally. So that is going to be I2 R3 minus I1 R2. Remember to multiply those two negatives, plus I2 R2 equals 0. Now I'm going to collect my terms. That's going to be negative R2 I1 plus R2 plus R3 I2 equals 0. And there is my second equation in my system of equations. Okay, so I have copied our circuit, our knowns and unknowns, and our equations over onto a new slide, and this is where the linear algebra comes in. We have two equations and two unknowns here, so we can write this as a set of matrix equations, AX equals B, where A is a 2x2 matrix. Now, if you don't already know this, I'm not going to teach it to you in this video. I'm not a math teacher, but we're just going to kind of go through the review here. So in this case, the A matrix is going to be 2x2. It's going to have parameters A1 or values A11, A12, A21, A22. That's going to be multiplied by our matrix X1, X2, and that's going to be equal to B1, B2, where again, A is a 2x2 matrix, X is a 2x1 matrix, and if I remember my linear algebra correctly, you take the inner two values have to be equal in order for you to multiply matrices, and then the resulting matrix has the dimensions of the outer two values. So that gives you a 2x2 matrix. And what you'll see here in equation 1 is this coefficient is going to be A11, this coefficient is going to be A12, this coefficient is going to be A21, this coefficient is A22, and then let's use a different color, I don't know, blue over here. This is going to be B1, and this is going to be B2, and your I1 and I2 are your unknowns. So I1 is X1 and I2 is X2. So this is, over here is just a more compact way of writing out these two equations that I have written out over here. So you can write this as R1 plus R2 plus R4, negative R2, again, don't lose track of your minus signs, negative R2 again, and then R2 plus R3 times little I1, little I2 equals B1, B2, which is VS 0. And again, we want to solve for these. These are our unknowns. So you can do that as X equals the inverse of A times B. And you can do this. I'm not going to do this calculation by hand, even though you can take the inverse of a small 2x2 matrix by hand with a graphing calculator or MATLAB or any other program that can do matrix calculations. And that is going to give you your values for I1 and I2. So I went ahead and did that. I actually just did it in Excel, which it turns out can invert and multiply matrices. So I'm not going to show that on screen here, but I plugged in all these values into the corresponding matrices and then did this calculation. That gives you, oops, wrong color. Always likes to default back to red. It's good weight. That gives you values of 1.146 amps for I1 and 0.611 amps for I2. Now, remember that we were asked to solve for V2 capital I2, which is the actual current through resistor R2. Don't get that mixed up with little I2, which is our mesh current. And as we showed on the previous slide, capital I2 is the difference between little that's a little I1 and little I2 because they were defined in opposite directions like this. So capital I2, the actual current through R2 is I1 minus I2. And when we plug those numbers in, I may have been a little lazy with the rounding here, but we get, thankfully, the exact same result for the current that we got in the previous video with the equivalent resistance method, 0.535 amps. We can then go on to use Ohm's law to solve for the voltage drop across resistor R2, which is going to be 0.535 times R2, which is 8 ohms. That gives us 4.28 volts, which again is exactly the same answer that we got in the previous video. And finally, the power, P2, I've been forgetting my substricts, is I2 V2, which is going to be 0.535 times 4.28, which is 2.29 watts. So again, all three of these are exactly the same values that we got in the previous video using the equivalent resistance method, but you notice that there were far fewer hand calculations here. You still need to, chug through this initial setup of the system of equations where, again, especially you're not doing as much algebra and substituting by hand, but there is this potential chance of accidentally inserting or forgetting a minus sign, which will then propagate and affect your final answer. But once you have set up these equations, then it's just a simple matter of using whatever program or calculator is your preference to do the matrix algebra and just solve for your unknowns all at once. These unknowns might not be the final unknowns that you were asked to solve for in the problem. Again, these unknowns in the mesh equations are your mesh currents, but then you can pretty easily use those mesh currents to solve for the parameters of any individual resistor in the circuit. So this can be a matter of personal preference. Again, you get the same answer at the end of the day. If you don't know or don't like linear algebra, you might find this method more intimidating or more confusing. But you can imagine as you expand to more and more complex circuits, so we only wound up with a 2x2 matrix here, but you could get a 3x3 or a 4x4 matrix. And just doing the linear algebra to solve for all of your unknowns at once typically gets a lot easier than what you saw in the previous video, where you're kind of chugging through doing lots of line-by-line calculations by hand to solve for your unknowns one at a time. So as you get towards more complex circuits, this method can be easier. In the next video, we are going to see a similar technique called node analysis, where instead of defining mesh currents, we are going to define voltages at nodes in the circuit and use those as our unknowns.